Okay, welcome. My name's Craig Wright. I'm loosely associated with Charles Sturt on and off. I lecture there and whatever else from time to time. And I'm part of a group of companies now running a number of HPCs to do with basically mathematical research in the commercial space. And as part of that, we're working with Charles Sturt University and one of the suppliers of our main suppliers of our hardware, that's down there in the corner, SGI. I must say big thanks to SGI, Silicon Graphics. For those who don't know who they happen to be, they're a big iron company. They put together a whole lot of machines, some of which we use, hence their little logo in the bottom. And hopefully this means we'll get some discounts next time I want to buy machines. Always good. And Charles Sturt University, one of my favorite universities. I taught with Charles Sturt for quite a number of years, as well as, well, I think doing about half their courses. So one of the fun things about being a bit of an academic junkie. And today we're going to start talking about programming on supercomputers. We're going to look at high-performance systems, high-performance computing, and then after this week you will be issued a username and password that will get you an SSH session onto a machine where you can jump across into one of our machines that are being set up and with a little virtualized area for all you guys to muck around in and hopefully not cause too many problems for me. It's the first time we've actually opened up even a virtualized slice of the machine to the public, so I'm hoping that we survive with 1,000 sometimes uni students and others actually having a login to the device. It's a little bit different going from a centralized controlled model to opening up a machine to the world. So we'll have to see how many people realize that that means they have some level of access, and hopefully the security controls we stick on the machine are good enough to, one, let you actually do the course properly, and two, to ensure that we don't have too many problems ongoing. So this is our first masterclass. We hope to actually have a few of these over time. This will be our introduction, and we'll start teaching you a little bit about why all this type of computational, well, development is necessary. So, as I said, thank you to SGI, thank you to CSU, and thank you to IT Masters. We have some of the people from IT Masters, James Hale and others, here on the line as well, so they can flag me and make sure
G'day.
that... hello, James. How are you today?
I'm good. How are you, Craig?
I'm
Hello,
very
everyone.
well. So we're going to hopefully get you through to a point where you can start learning a little bit about parallel programming here and understand how this all works. So these lectures and tutorials will basically start you on the fundamentals as we have it with advanced programming methodologies. Now, first of all, we'll start on a little bit of course structure, our introduction. So we're going to start this week just going over what high-performance computing is, going into what a supercomputer is, how we're going to start you training and preparation for the next 4 weeks, where we start you after this week hands-on on the system and actually doing some tutorials and everything from Hello World up. So yes, we even start you on Hello World, but that's just the way things are in the general world of C. So we're going to prepare you in this. Next week, we're going to really start covering off more and more of how you do that. So we start our first lab training. So we're going to go over the Intel C compiler and how that works on a massively parallel system. And in that, hopefully, start to teach you what is, well, what fundamental differences there are when you're talking about many core systems. Now, for those who haven't worked with either CUDA or MIC type architectures, these can be very different to many of the normal multi-core systems. In particular, we're moving away from small numbers of clusters or cores. Even on some of the newer hyper-threaded systems per CPU, you're talking about maybe 24 hyper-threaded threads. Compare that to sometimes individual cards on CUDA systems with up to 1,000 or so threads, or around 120 per MIC card, and the way that you have to actually program these systems is going to be different. So we're going to start thinking about how we develop cluster-based systems, and this is really the future of where we're going to be going over the next 10, 20 years. We're not going to get bigger and bigger processors. What we're going to start doing is clustering more and more so that we can start meeting the future of where systems are going, the future of Moore's law, and actually stay developing that. We're going to move into a more clustered infrastructure. So in week 3, we continue looking at power grids, thread programming, parallel computing overviews, and also look at a little bit on Intel Fortran compilers. We're still mainly working on C and C++ here, but I'm just going to introduce the differences. We're going to look at OpenMP. For those who haven't tried it before, there are different standards for multiprocessing, and OpenMP is a nice free one you can get to. There's the Intel ones. We're going to look at programming R. For those who haven't already done it, R is a statistical language, and we're going to look at how that applies to many integrated cores. So in particular, the Xeon Phi card. We're going to look at scheduling algorithms and how they work, programming and executing using a batch system. One of the things you'll find is not many people are going to have complete open access to an HPC, so they're going to have to actually share the system, and that's a fairly common way of doing these things. So it's very much like an old-fashioned model where you have mainframe access and you're doing program time sharing. And then we're going to look at some particular issues with the Xeon Phi, with clustering, not just one machine, but how we work across multiple machines. Look at some different cluster architectures, how you can develop that yourself, how you can develop your own systems at home, ways of exploring and testing and implementing this, either on multiple Raspberry Pis, multiple systems, or even creating your own cluster to play with, and then looking at some of the different training options for OpenMP, MPI, etc. Now, all of these things will take you a lot further into parallelized systems than you would generally get if you're developing code for a laptop or web system or whatever else. When we're talking about these types of computer systems, we are splitting many, many parts of a problem off. So in solving mathematical problems, we might be splitting the possible solutions that we want to test in ranges out. So one option would be, if we're trying to solve a mathematical problem, we have the range of inputs from 1 to 1,000,000, and we test it 1 to 10, 11 to 20, etc. between the different cores. And then we send back the results when something actually finds the answer. So that's part of what we're doing in sharing all of this information. So overall, we're really breaking problems down and splitting them across many systems. So we've covered a little bit about what we're going to do, and we need to look at what supercomputing and HPC actually means. Now, if we look at the origins of HPC, we go back, way back to Cray and other machines back in the 70s, and we find that we have machines that, well, are now superseded by watches or phones or other things that at the time were large, sometimes took up rooms, used huge power draws, and for now did very little. Something that would not even handle what an iPhone does. However, this is where all of this will go. In 10 years, 20 years' time, everything that we're thinking of will be far more advanced and far more powerful, just following the standard curve of Moore's law, and we can expect that we will have desktop machines running in the hundreds of teraflop, if not petaflop ranges in that sort of time. Where that will actually take us, it becomes difficult to understand. At the end of the day, that sort of computational power in everyone's hands changes the dynamics of everything we're doing in society. So we've ripped off some lecture material from Silicon Graphics. We've got some from a couple of universities, and I'm not taking full responsibility for putting it all together. We've basically done a mashup of different course material that we're allowed to do with some labs and access so that you can hopefully learn all of this well. So supercomputing, we're talking about the biggest fastest computers available at the time. So right now, what we run is not going to be a supercomputer in 10 years' time. I read an article just the other day complaining about a supercomputer down in Texas. The journalist was saying only 10 years later, this machine is no longer used and has just been trashed. We spent $20 million in this state on it, and now nothing's happening. The reality is a supercomputer generally has around 2.5, maybe 3 years lifespan. It can be updated, it can be upgraded and go for longer, but because of the power draw, it's not going to be cost effective to keep it going. And one of the biggest costs in there is actually looking at how much electricity is being used at any time. And it's very, very well costly to power these things. It's not just the hardware, it's the ongoing operational cost that makes a supercomputer expensive. So, rule of thumb, a supercomputer is typically at least 100 times as powerful as your PC. The top 500 supercomputers, we're looking at machines that are in the hundreds of teraflop range now. And it's not actually that expensive to build one of these. It is more expensive to run it. If you start thinking about some of the new high-end NVIDIA and GPU cards, you can start putting together maybe 8 to 10 or even more, depending on the cards, teraflops per host node. If you have multiple newer cards, 20, sometimes even more. With the PHYs, you could maybe get a single node with 8 teraflops. How much space isn't always the case that you need to worry about. It can be, depends on what your economic constraints are. Heat is one of the big ones. Location then becomes important. Many machines are now starting to move towards oil cooling. They're starting to move towards being powered in areas where there is more easy access to electricity. And the reasons for all of this is just the cost. So high performance, high end cyber infrastructure. There's also high processing computing. It's really very similar for each of these. So the different terminology, of course, like everything else in IT, really comes down to what an individual actually wants to call it. High performance or high processing depends on what you're actually putting through the system. It varies depending on what use you're getting from it. And we're not in anything that is going to remain the same for terribly long. In HPC, we're looking at something that is fast and large and processes and crunches a lot of data. That's really what it's about. So we've got the elephant and the cheetah, and both of these things go together. So you get a choice of what you get in many things in IT, and size and speed together form the core of a HPC. So you're not going to carry these things around anytime soon. So, size. There are many problems that are not going to fit on a laptop or a PC or even a workstation. Some of these take many gigabytes, terabytes, etc. of RAM. More than a few gigabytes of just drive storage. I mean, I know we have 6 terabyte drives and all this stuff, and my my desktop machine now has storage of 30 terabytes. So we're moving very quickly. Speed, problems here, something taking a month on a PC might only take an hour. There was recently a test on one of the large American computers where what they did was they loaded up quite a number of mathematical problems and they solved many problems at once. What they did was they loaded around 1 billion problems that needed solution and just loaded them all. Now, of course, it's going to take some time for people to actually sort through those and figure out what they need, what they want, but now they have a sort of collection of solved mathematical problems, and that actually means quite a lot ongoing for things like simulation. So simulation, physical phenomena, weather forecasting, galaxies, oil reservoir management, data mining. So we're not even looking at needles in a haystack anymore. We're now looking at the fragments of needles across many haystacks. So gene sequencing, signal processing, detecting storms, trying to actually model weather, visualization, analysis of pictures, analysis of cryptographic problems, etc. All of this becomes something that we can start doing pretty well using a HPC. So in our case, we're modeling financial systems. We're modeling the interaction of different financial systems, things like oil and whatever else against Bitcoin and the blockchain. One of my key focuses being, or foci being, that I'm actually looking at risk interactions and how we can actually build a better financial system, and that requires a lot of data. So we're working with a number of companies that have access to some of that data. We're then running testnet simulations for changes in the Bitcoin blockchain, how that might occur, what may happen. And it's not only then, in our case, if we take one example being analysis of the blockchain, that's in tens of gigabytes already. But if we do a Monte Carlo simulation where we run that in 10,000 different formats in memory, what we're taking is 10 gig times 10,000 and loading that into memory and analyzing it and trying to do it in real time against different scenarios. Then you start doing network analysis of that, how it's changed, and the n-1, n-2 relationships, and you start actually not only getting a linear but an exponential growth. So rather than 10,000 connections, you have 10,000 by 10,000 connections, then 10,000 by 10,000 by 10,000 connections, and very quickly you find that the amount of processing is going to grow extremely quickly. So we have two issues. First one, tyranny of the storage hierarchy. It's becoming more and more high density for storage. We're running a number of file systems underneath everything, and then trying to make it look like a normal system on top of that. The underlying one, and the majority of what we have, is either Lustre or Gluster, although I'm also exploring a few other systems. And Parallelism, which is trying to do multiple things all at the same time. So we break our problem into lots of little tiny problems. So where we're going to go next from all of this, we're going, over the weekend, I'll give you a small exercise on SSH. So before this time next week, hopefully you would have logged into the system, checked that you can access it, checked that everything's working, got back onto James or one of the other guys and said that your access does or doesn't work and all the rest. One of the things, we've never actually opened up 1,000 plus people, well, ever. There's over 1,000 people on this course, and hopefully the scripts to set up all the environments have worked correctly, because it's one thing to open up access to a few staff members, it's another thing to start rolling it out to 1,000 people. So we're going to find out how well that works over the next few days. On top of that, we're going to be going into demonstrating the operating environment next week, looking at how batch workflows work, and a little bit on the electricity bill. So one thing that you will find, and it's in the reading material for you, is just how much these things cost. And it is phenomenally large. So we're looking at way over tens of thousands of dollars a week. In fact, over $100,000 a week just running these things. The electricity bills are huge. Hence, making sure that they're actually being utilized correctly. Many organizations actually turn their machines off after they get to a certain age, because it then doesn't become economically viable for them anymore to leave them running. The sole reason here is just how much it ends up costing. If you start thinking about the cost of a machine that you get 10 years ago to now, the real issue is just how much power consumption they have compared to what grunt they have. So preparing for this course, we're going to have weekly lectures. This is the nice, easy intro one. Gives you a little bit of reading material. We're going to assume that you've got some level of C programming and knowledge of C. Hopefully a little bit. If you don't have too much, I'll try and walk through some additional sources you can go to. We have some additional reading before then, and there will be 4 online lab sessions. So you're going to practice programming on each of these different sessions, and as you practice, hopefully you'll find out, well, the difficulties in how this actually works. So we've provided some additional week 2 reading. We have NVIDIA C programming guide, a building open MPI guide, and the Intel MPI guides on Xeon Phi. So a little bit of reading to get you going. Now, got a question there. Is the final exam a question and answer or some sort of final lab assignment? We're actually going to make it a final lab assignment. So week 5's, or the lab number 4, will be actually getting on there and doing something, and we'll test you on that. Now, on that, we're actually going to give away a number of Xeon Phi cards as part of this course. So the top 10 people will be given their own Phi card, so with some instructions on how they can set it up on their own machine. You can actually run a Xeon Phi in Windows, and I can point you to some of that, but it's much harder than it is on Linux, or unfortunately, or fortunately. I actually like Linux, but I sit here on Windows most of the time because some of these tools don't work terribly well in Linux, but that's life. So we're going to cover off how you set up your own for those who are lucky enough to win one, and going forward, I'm also going to be offering some access to people who come up with good ideas around the cryptocurrency and financial risk analysis space. Potentially, one of the things we're going to do for some of the people who come up with the top ideas and whatever else after this course is slicing off up to around 100 teraflops dedicated per person that we can give away for the right sort of idea. So it's a strange sort of incubator in a way. If you have a good enough idea, whether it's pure or applied research, I don't really care, but we're going to allow people to have that as a research area on this system. So, the next big digital revolution. The trend is more towards distributed system, microarchitecture, hyperdensity, and really consolidated clustered services. Even when we're thinking about what we're running on our phone, we're getting more and more clustered chip infrastructure. So the Samsung I have in front of me is a many-core infrastructure in itself. It has 16 cores, and well, really that's an amazing amount of computational power compared to many of the servers I used to run even a decade ago. Having run a number of hosting and other services for email, web DNS, etc., from the 90s on, my Samsung phone actually has more power than some of the web servers, more storage than some of the clusters I used to run. And when you start thinking about this, this is an incredible change to where we're going. And just remember, as I said, in 10 years' time, we're going to have more and more clustering as we actually start moving towards machines that have many integrated cores just to run things generally. So, we have, what is a cluster supercomputer? Well, every computer that is high-end now is moving towards a cluster infrastructure. So we have the old Johnny Depp bit there, what is a ship? So our supercomputer is not just the bits. It's not just a PHY card. It's not just memory. It's not just a group of all these machines hanging on together. It is the entirety put together. You can't really take one part out and say, well, it's not a supercomputer or it is a supercomputer or whatever. It's the whole lot working together. So our cluster is the integration of all these things. So a cluster needs many small computers. These are what we call nodes. So the terminology here is when you get onto a node, these hook together in an interconnection network, an interconnect, and that is what allows the main computer to send everything off and have it processed and come back to you. So our interconnect is the way that all of these different machines hook together. So we'll log into an access node, and from that access node you load up a module that is then run across many different cluster nodes. So we need software that allows these nodes to communicate over the interconnect, and that's what a cluster is. They're one big computer. So we can actually split things off in a supercomputer as well. We can give virtualized access, and we can only issue part of a supercomputer. We can lock that down. Hopefully that actually works properly when we do it. If we do it wrong, then you give away far more than you plan to, but we're going to find that one out. And in a way, it's a security test. Opening all this up to 1,000 plus unknown people, or semi-known, or whatever else, is going to be a very interesting security test for us to see how well we've actually locked down the access to issue this. So let's go over some of the typical primers on what we have in a computer hardware. We have a CPU, primary storage, secondary storage, input devices, output devices. I'm hoping everyone knows what all of that happens to be by now. Our CPU is very, very poorly called the brain of the system. It's the control unit. It loads data from memory, acts as a way of branching where things go, performs simple calculation, holds registers, data resides there, what's being used, what's been swapped, what's been processed, etc. We have main memory, RAM, random access memory, where our data resides when it's being used by a program that's currently running. The reason here is, of course, it's much faster than that disk-based or flash storage. And we have cache. This is where we have really fast access memory and the things that are about to be called or have been recently used. So primary storage is volatile. So anyone who remembers doing any forensic exercises, I've done some of these in the past, including with CSU, looking at memory forensics, you know that it changes very quickly, and if you're not there and grabbing it fast, then it will disappear and the power turns off and it's hard to get access to. We have secondary storage. These are our future storage, our long-term storage areas. Everything from hard disks, CDs, Blu-rays, magnetic tape, floppy disk, all the things that are old, right up to new things, all the different forms of drive storage, etc. now. Input-output devices, keyboard, mouse, joysticks, scanners, monitors, printers, speakers, 3D printers, you name it. We have our storage hierarchy. So we have fast, expensive, and slow, cheap. Now, you get a little bit of register memory, not a lot. We get a little bit of cache memory, not a lot. Then we get more and more main memory, hard drive, etc. And of course, the slowest of all this would be the internet in some ways. We can map and store everything in the cloud, but then we're going to call it back and forwards, and depending on how fast our internet access is, we're going to, well, really slow down access to files compared to what we have locally. Even hard drives can get quite quick these days, especially if we're doing shared RAID or anything like this. We can have fiber channel or other faster means of accessing our hard drives. When they're shared over things like RAID 60, RAID 100, etc. on a hardware level, they can be very quick. We're talking maybe 24 gig per second or greater for individual parts of data, and if we can have that between machines, sometimes we can even get up to around 50 gig per second access. So when we're talking about HPC type systems, then we are talking very fast access. So RAM, CPU, whatever else, to this we have a number of different bottlenecks developing on our system. Sometimes we get faster than the 15 gig per second, depending on what we have. The new buses can actually be faster than this. And we can have multiples at once. So parallelizing these can actually make things a little bit slow or fast depending on how we do it. So main memory and the CPU, well, we have faster or slower RAM depending on how much we want to spend. The more we spend, the faster it is. Anyone who's had a look at some of the newer RAM chips will know just how expensive they can be, but also comparatively how quick they are. But at the same time, this is why we have cache. So this is closer to the speed of the CPU, and in any of the modern cards or chips or whatever else, the NVIDIA cards or the Intel Xeon Phi cards will actually have their own memory and cache on the cards just to implement quicker processing. So some of the Xeon Phi cards have either 8 gig or 16 gig, depending on the model, sitting on the card that you can directly access and play with, apart from the many different cores. So let's go into Australian grid computing. So this changes all the time. We have us here in Australia punching way above our weight. We're sort of up there in the number of systems we have internationally, and I think we're actually going to change that a fair bit next time. The reality of all this is we've just completed a whole pile of upgrades over the last few weeks. Lawyers paid for it and all the rest around a month ago, and people in data center have been well, running around doing some upgrades and everything like that to take us to a new system. What we've done is we've integrated our Supermicro and SGI systems into one big machine. We used to have two separate machines and architectures, and we're experimenting with a combined system at the moment, which is an NVIDIA CUDA-based system, as well as the Intel Xeon Phi on a shared interconnect, which is fully meshed. So not just a torus or anything like that, which I'll send some links to explain how the meshing and everything is done, but not just a group of separate machines, but one group of machines that can talk across different architectures. I don't know how well that will actually work, but we're going to find out. One of the fun things about all of this is you get to experiment. And that has taken us to 3.9 petaflops. And a petaflop, well, if you know what a gig is, 1 million gigs, so 1 million gigaflops. And 3.9 petaflops is probably about 1 million times an iPhone. It's 1 million times one of those old Cray machines. So getting big, and that's just the way these things work. So parallelism means multiple things being done at the same time. Now, Richard's asked, but the real question is how many bitcoins a day? Well, in the old days, it would have been a lot, but interestingly enough, a 3.9 petaflop machine that is based on a combination of CUDA and Xeon Phi is a very, very poor mining machine. The ASIC architecture, the specialist designed hash chips that have come out actually work far, far better than any of the CUDA machines do. So if you wanted to do this, you'd find that the electricity actually costs more than the Bitcoin you're mining. So ASIC miners are very good, but they exceed for the hash power everything we're doing. So I've got another question. Could you tell about the current situation of HPC Gluster supported cloud computing? Well, Gluster is a file system, so I guess the best, Gluster is a distributed file system that works really across different machines. Most of ours are still on Lustre. I've been experimenting a little bit with Gluster. Very similar, Gluster with the G versus Lustre minus the L, different ways of creating one very big shared fast file infrastructure. Now, interestingly enough, in the future of cloud computing, this could actually be a means of sharing some very large files across many distributed systems, not just like we have with a same core, same architecture type device, but potentially moving from clusters to grids so that we have lots of different machines. So it's going to be, I can't really give you an answer at the moment. I can point you to cluster with Hadoop, cluster greater than or equal to Hadoop. It's a hard question. Hadoop is changing very rapidly, and Gluster is changing very rapidly in some areas, and neither of them are really where they're going to end up. I guess I can't say where they're going to end up. The underlying hardware sort of integration is changing so rapidly, and it's getting so quick and so fast. We're not just talking petabytes being supported, but moving towards exabytes and above. And both of these, Gluster and Hadoop, are supporting that. If James gives me a reminder, I will load a little bit of research that we've been doing between different file systems up for everyone this week as well. We have looked into a number of different distributed file systems, and it's probably better than me jumping in here and sidelining it for the moment, but giving you something to read on those. It depends on a number of things. The size of the file, how many files, how quick you need access, whether it's archive or not, all different things come into it. So it's not a single answer. That's the difficulty in answering this. There's not one answer whether you use Gluster, Lustre, Hadoop, etc. It depends really on what you're doing. If you've got lots of small files, you'll choose a different solution than if you're trying to have a lot of large files that hardly change. So, but I'm sure James will remind me, and I'll load that research up for people to have a read of. So getting back to all of this, okay, we're going to look at how we split things up. So what we hopefully do is, as we have here, one big fisherman will catch less than our lots of little fishermen. So we're going to break things into our jigsaw puzzle and see how we can really put it all together. Serial computing, we want to do a 1,000-piece jigsaw. We do it one piece at a time. What can we do? We put a piece down and then we find a piece that fits and another piece. Whereas if we look at shared memory parallelized systems, well, we're going to start communicating between all of these simultaneously. So we basically make things go faster. So we think about how we're going to do this, and we split up things so that we're actually solving many smaller problems instead of one big problem. So we're going to start thinking about how we do that. So in a serial system, when we're doing things bit by bit, then we don't really speed up as much as if we're doing lots of little problems. So when we've been increasing our throughput through a bottleneck, we can increase the amount we send down that line, but we don't get as much as if we start also putting more lines in. So what can we do? We split everything up and we solve it by decomposing our problem and then reassembling it. There is some actual cost in doing this, of course, because we have to work out how we split the problem up. In distributing our system and splitting it into multiple parts, then we don't just suddenly double our computational power, because there is a little bit of resource management that has to go into managing this. But what we can start doing is doubling and doubling and doubling, not just 2 processes or 4 or 8 or 16, but we can very quickly start adding more and more very quickly. So load balancing these is the difficult aspect. Now, what is load balancing? This is ensuring that everyone completes their work at the same time. So we don't want someone finishing way ahead of the others. We don't want one person finishing their job and waiting an hour to get a little bit more information. So we want to think about how we split our board up and how we get the pieces to ensure that these things actually work at about an equal rate. So load balancing can be easy. We can just split it into quarters, or there might be different ways of doing it. It can actually be extremely difficult. As we see between the 2 options, we have easy load balancing or hard load balancing. But sometimes the algorithms to work out what is the hard option actually give us far better results over time, because they're going to actually waste far less time. So a little bit of a segue into Moore's law, first of all. So this goes back to 1965. Gordon Moore was one of the engineers and senior people at Fairchild Semiconductor. This is now part of what has become Intel. So he's noticed that you could effectively double the number of chips, transistors on a chip every 2 years or so. It's actually a little bit quicker than that. We're actually doubling about every 18 months is what it's worked out to be. And that effectively meant that computer speed and storage capacity is going to be increasing at that type of rate. So as the transistors per unit area actually increase, then so does the overall speed of processing. So this is something that is fairly predictable. It's actually worked out every 18 months or so we double. So what we're looking at here is number of gigaflops and Moore's law. And Moore's original calculation was actually a little bit under what it's come out to be. So we find that we're actually increasing a little bit faster than we estimated, strangely enough. So we find out that instead of every 2 years or so, we're doing about every 18 months. Now, what you see is a logarithmic scale there. So it goes 1, 10, 100, etc., so that we can not have a big exponential curve. We can see that on a logarithmic scale, it's fairly much a linear growth. What we have is down from around the early 90s, in the start of the top 500, we had in the order of maybe 50 or so gigaflops. 50 gigaflops isn't a particularly great PC anymore. If you're running a nice new Intel or Mac machine or whatever else, chances are you have more than 50 gigaflops sitting on your laptop. If you look at the cost from these machines back at the start of the top 500, that laptop processing would have cost you maybe $5 to $10 million. So question, Moore talked about the number of transistors per square inch because of the computer parallel processing, more CPUs. That sort of doesn't add up, does it? Well, what's happened is we got to a point where making faster and faster machines actually created too much heat and caused other problems. So what they've actually done is increased the amount of transistors by splitting into different layers and different chips, and effectively splitting up into different CPUs. So when you've got that multi-core machine, it's really like having 12 CPUs right next to each other with a shared bus, etc. At the same time, we have the drive storage is increasing as well. So we find that the amount of drive storage has not quite as fast, but it's increasing remarkably as well. I mean, on our systems, we have, I think, 600 petaflops worth of storage space, and that's enough to actually hold every book printed by humanity ever, several times over. So it's amazing how much data you can add. And one of the deals we're doing now will be, we've got two, one with a finance company and one with a gambling company, and it would be very, I'm really looking forward to actually modeling all that data. How to send my idea re-blockchain. If you want to get on to James, if you've got any ideas, and at the end of this, one of the things, I'll give some details about what you can put down and what you're looking at testing, and I don't know, apply, but however you want to put it, how you can sort of make a proposal for us for what you want to test and jump in and do it, then I'll let James filter all that.
We can do this via
Okay.
the assessment submission system in the learn.itmasters.edu.au portal. People will put up something there, and you can put it in your submission. You can put it as private or public.
That'd be good. So anyway, back to this. We have our speed. So we're looking at the advent of the first teraflop type machine. Now, a teraflop is around what you get on one of the older Xeon Phi cards now, by itself, or on a low-end GPU card. Some of the high-end GPU cards will have 8 teraflops now. Host details, etc. will be put up this weekend. I'll be going over a little bit of a how to load and get access tutorial, so that will be going up on the site. Is the idea submission for only a blockchain idea, or can we submit an idea for everything, for anything? Well, if it's a good enough idea, I'll listen to anything, but it's generally around what we research is finance, money. It doesn't need to be blockchain, but risk, derivatives, any of those sort of ideas. But one of the things, I mean, I'm actually looking at a climate model at the moment for one thing we're doing, but it'll be commercialized rather than just predicting little red spots and going awful climate change stuff, more looking at predicting where land values will change because of changes to weather patterns. That would be a more interesting one in my opinion. But anyway, back to this. So we're looking at teraflops, then to petaflops. So we're looking at around the petaflop sort of mark just a few years ago, around 2012. We're already now with the Chinese supercomputer there over 30, around 34 plus petaflops, and there are proposals now to actually build a 100 petaflop machine, and I'm not sure where that will be. We've put in our submissions for the top 500 last weekend, which took us to 3.9. Which I was very chuffed with. 3.9 petaflops is damn big. It's 3 times what the NSA used to have for their supercomputer that monitored everyone's phone number around the world. So it gives you the sort of processing power that these things can have. Then as we go up in time around here, we're looking at actually moving towards the exascale on systems. So somewhere in this point around 2018-19, we should expect to see a more common exascale type architecture. So that's coming. Now, what we're looking at, number of cores, we have our HPL benchmark here at the nice little Chinese one with 3 million CPU cores. It's a lot of cores if you think about it. And that compares to the 1,000 core machine at only 60 gigaflops way back at the beginning. So we have grown. So the number of gigaflops you see, how that increases, and Moore's law, how that increases, we're actually doing better than we expected. So Moore has been fairly correct in some ways. The number of transistors has increased. It is improving remarkably. So over the nearly 40 years we've been looking at this, we have increased 1 million times. And if you think where we are now, 3.9 petaflops is basically listed as 10% of the processing power of the human cerebellum. That doesn't mean that by having 10 of the things we're running that you have a human brain. What it means is all up you have the sort of processing power with the right software there. If you think about that, that is potentially in 40 years, machines like we're running could be 100,000 times computationally more dense than a human brain and interacting together. Where that will go, who knows? So, Moore's Law, CPU, network bandwidth, we're finding that is going up way more than Moore's Law. RAM, yeah, it's a bit of a bottleneck. Unfortunately, the amount of memory and where that's going hasn't increased as much. The cost is one of the problems. You can actually build high RAM machines, and our machine has well over 100 terabytes of RAM, but RAM is expensive. Network latency, we are improving, but not as much as would be good. The bottlenecks there start coming into play. So parallel systems actually help with latency in that you can split things apart and not have as much transmitted over each network. That's where you start getting peer systems and everything talking together. With the InfiniBand systems we're looking at, our latency goes as low as around 4 to 6 nanosecond latency in between the machines. So is this data based on US or worldwide? Worldwide, and depends on where you are. If you have a good enough internet connection, then things work. If you don't, can't say much. Okay, so looking further, software is the real bottleneck. Software increases far slower. It's actually the hard bit. So Moore's Law on gene sequences, one of the people who works for us, Ignatius, works also in protein modeling, and you find that some of these things actually have increased remarkably fast. So what have we got? We have 1 teraflop. That used to be a room. I remember working for the Australian Stock Exchange, a whole lot of old VMS machines, a whole lot of other things, processing data for brokers and all the rest. A room. We have ASCI Red, basically a room. And that moved till 2002 with a row, so we have 11 racks to make a row. Now we have a Xeon Phi card, a Kepler card. Both of those will give you a teraflop and eventually a chip. So why bother? Well, it's clear that it's going to actually be a difficult thing to learn everything that's happening here. It's not really you jump on their code for an hour and suddenly you know everything. But this is your insight into the future. The great thing with HPC is you start to learn where computing is going. If you start to think about what you need to protect, how you protect it, and what you can do, then this is the future of technology. And understanding the future of technology now, a decade before everyone else gets to it, that's a valuable skill. Knowing what the bleeding edge can be, knowing what can be is very valuable. And on top of that, you get a whole lot of problems that you can start to solve. So you can look into things that we haven't been able to solve in the future. In the future, we'll be able to do more and more. You can tackle bigger problems. You can do it faster. We can create more data, analyze more data, and know more. Instead of doing something that will take years to do, we can actually do things ahead of what we expect. So the future is now. Now, this is always going to be true, and supercomputing is something that will be on your desktop in 10 to 15 years, depending on how advanced you are. So if you are experienced with a supercomputer, you know how to program a supercomputer, you're going to have the skill set that is going to allow you not just to have a job now, but in the future. So we're going to point out a few different areas and where you can learn these things. Looking at week 2, we'll load up some additional reading there. We're going to look at some different sites like the Grid Computing Center, HPC University, other workshop series, the NCI training exercises here in Australia, and then we'll look at loading your Lab 1 and getting you on an actual Intel C compiler and starting to learn the documentation. So you should have that documentation. Start having a bit of a read. We're going to play with the MIC cards primarily for this. We're going to generate some compiler reports and see how they vary and what sort of options you get. Look at different compiler directives, how you can vectorize your code and get it in line, etc. And really start understanding and pulling apart what we're doing. So that's really it for week 1. So this is our intro. James has material up there now. We wanted it a bit earlier, but we've been running around madly, and I've just been in Canada and here, there, and everywhere. So apologize for not getting you things earlier onto the site, but it should be there now. And that's where we're going to be moving from. So in the coming days, you'll get access to start playing with some of these things. We'll give you the lab exercises. You can start experimenting and trying the different compiler options and see how you go. So that's really it for now. So thank you for attending, and thank you, James, for helping out and making sure all this works smoothly.
Thanks, Craig. Thanks, everyone.
So hope you enjoyed the first lecture. This is our only really non-technical one. After this, we're going to actually start getting down and dirty. We have a lot of material there that we're going to be loading up from SGI. Silicon Graphics have been very good in giving me a lot of material and helping out a lot. The wonderful people at Silicon Graphics have a good service mentality. I can't give them enough praise, which I won't go into it here, but you probably guess if you look at any of my Facebook things, other companies who didn't support us in the beginning, I bitch about. Those who did support us, I don't. So glad you're looking forward to getting down and dirty, Richard. So wonderful. Okay, at this, again, thank you all for coming, and I hope you enjoy and learn, and I hope it all goes well for you.